All right. So our next speaker is joining us from Oxford, where he's working on his PhD, and he will be talking to us about medical image analysis, and especially tackling some real-world issues related to federated learning. Please welcome Pramit, Saha.
Thank you so much. Hello, everyone. I am Pramit. I am a final year PhD student in the Department of Engineering Science at the University of Oxford. And I'm just going to submit my thesis on federated learning next week. So wish me luck. So today I thought I'll talk about like a brief overview of what we are doing with federated learning for medical image analysis at the Oxford Biomedical Image Analysis Cluster. Instead of going deeper into one particular project, I'll just give you an overview of different tasks that we are trying to solve. So I'll talk about three main topics. First of all, our real-world collaborations, international collaborations with different countries using federated learning, then tackling a few practical problems in medical image analysis using federated learning, and then federated learning in the age of foundation models. The first work we have is a collaboration between the UK and Indian sites, hospitals, where you'll see we are working on a fetal ultrasound video anatomy detection task. And we have 2 clients in Indian site and 2 clients in UK site. And we are working on detection of anatomy. So you can see there are some anatomies which are quite rare, and it leads to some class imbalance, some data heterogeneity, as a result of which we are trying to come up with some ways to tackle data heterogeneity. So we propose a client-level class imbalance mitigation technique where we sort of get the data distribution of a client and get the difficulty metric of a given client, based on which we guide a focal loss function that deals with the class imbalance. And as you can see, it can locate the anatomies quite well. The second work we had is a one-shot federated learning, where we were trying to tackle congenital heart disease detection with Australian and UK sites. And as you can see, there's quite a bit of domain gap between different sites. And so if you train your model individually on individual sites and you test on your external sites, you'll see that the models 1, 2, and 3, which are individual site-specific models, don't really work that well. You have to generalize. So we do federated learning using a one-round or one-shot aggregation for this. Moving on to some practical problems, we dealt with missing labels problem. So we deal with clients where we have labeled clients and we have some clients with unlabeled data, and how do we train supervised and unsupervised models together in a collaborative fashion. We proposed a very simple technique where we say, how about we isolate the aggregation of the labeled clients and unlabeled clients so that there's no mismatch in gradients. And we add another extra step of a client-based self-supervised pre-training before we run the training every time. That helps us to adapt the models. Now, what if we have already trained our models and now a new client joins in, right? So we have client-specific personalized models and now a new client joins in, and we want to tune these personalized models to our new client as a sort of test time adaptation. So we are trying to align the gradients of these different client-specific models to my target model so that I can adapt this or align this source models to my target models for federated learning. Now, what if not just one client? What if clients keep joining in an incremental fashion? Our task is to keep learning from the new clients, as well as we need to preserve information from the previous clients, right? So for that, we use a knowledge distillation-based method in the server, where you can, as you can see, if clients start joining in, our client 1 and client 2 are specialized in segmenting pancreas and spleen, and the new clients that are specialized in kidney segmentation and liver segmentation joins in. We are trying to keep up with the new segmentation that the expertise is brought by the new clients, but we also try to preserve the information that we learned from the previous clients. We're looking at a similar segmentation problem where we work on this brain tumor segmentation or brain stroke lesion segmentation from different types of modalities in brain MRI, because you can have T1, T2, FLAIR, et cetera, different types of MRIs present. And so we have to generalize across different modalities and different pathologies across different clients. So we propose a sort of random modality drop during training so that the model becomes robust during the collaborative training and can generalize during testing. As you can see, for example, our method that we call FedUniBrain has better performance, and it performs closer to ground truth with respect to the models that are trained individually in different clients. A similar problem on multimodal federated learning where we deal with language and vision. But in some clients, you have language missing. That is, you have chest X-rays in some clients, that is some hospitals, and you have reports and chest X-rays in some hospitals. So this is the problem of modality heterogeneity. How do you deal with this kind of heterogeneity? So we tackle this in different aspects. So we try to play with the self-attention, controlling the interaction of language and vision. We try to generate text whenever text is not present in a sort of generative way. We try to constrain the federated learning setup in the client level or the server level by adding some regularizers so that the models come closer to each other, even though you have modality heterogeneity in the input. Now, using foundation models, we try to fine-tune foundation models in a federated learning setup. And so what we look at is how do we use adapters, which are one of the main ways of fine-tuning foundation models. We find that if we have different clients that specialize in different modalities and tasks, that's a problem because your adapters learn different information. So what we propose is to reduce the oscillation that you can see here with the adapters. We propose to align the adapters first before aggregation. So first you adapt the adapters, or you align the adapters from different clients, and then do the aggregation. So just an alignment before Fed average helps us a lot. The last work that we have here is basically respecting the client-specific resource constraints of different clients for fine-tuning foundation models. And we select the layers. So it's a selective fine-tuning where we select layers based on the client-specific resources. And we do that in a client level using neural tangent kernel eigenvalues to select which parameters are more important. And we also do it on the server level to select how can we diversify the layer selection to have more information. That's it from my side. Thank you. So I talked about the real-world collaborations that we are having, enabled by federated learning and Flower framework, and also the main practical problems that we deal with in federated learning. I just wanted to give you an overview of the works that we have been doing in our biomedia cluster. Thank you so much.
Thanks a lot, Pramit. Do you have any questions? Yes. Oh. Oh, we also have one here, maybe. Oh. Yeah.
Thank you. Thank you so much for your talk. It was really interesting to see. I'm also working in medical imaging, so I was just wondering, how did you go about really, sorry, I think this is better. Yeah. How do you go about setting up the real-world network? Because we also had a lot of problems actually in setting it up real world to go actually from a simulated setting to a real world setting. I was just wondering, like, how did you deal with the communication layer, the hardware, and making sure that actually the clients have sufficient hardware, and also to have someone maybe in place that can restart your computer or stuff like that?
We had to go through all of those. We had to have data scientists in the different clients who could set up we connected via VPNs and stuff. We had servers, so we had to do all those. And then we use the Flower framework to sort of do the federated learning stuff.
Okay. Super interesting. Congrats.
Thank you.
Yeah, thank you for the great presentation. Really awesome to see that you got the real-world use case working. So about the combination of supervised and unsupervised training. So how do you deal sort of with data poisoning situations? Because if it's unsupervised, I mean, any person in any hospital could inadvertently upload the wrong scan or upload a picture of the beach rather than the medical image.
Yeah, thankfully we worked on pre-processed data where we had people who went through the data and made sure this is clean data. And so we did go through a quality assurance program to make sure that the data we have doesn't poison the results. But that would be a different scenario where we can deal with it. But thankfully for this one, we didn't go to that. We just assume that the data we have is not noisy or is not poisoned.
OK, thanks. Yeah, congrats on the project.
We only have time for one short question. Yeah.
One quick question. I just checked your work is just to testify your approach based on the medical X-ray images. Have you tried to fit other types of medical images, such as the patch, medical patch image, or mix different types of medical images put into the same model? Is it possible to give a same result, same accuracy to your model?
Doing what? Sorry, what is the alternative?
Yeah, my question is just I just see you utilize the X-ray image of lung disease into your model. Have you tried other types of medical images to testify your research?
No. That's primarily because we have lack of vision language data sets in medical area. There are a few CT images that I've seen recently, CT data sets that have language and vision, but we are still about to try. I haven't tried it. I've just tried with the chest X-rays.
Okay, I also checked you have to test the video, medical video. So how to process the video? Do you need to select some specific frame of the video or other processing steps?
No, we work on normality prediction. So we first do a self-supervised training of different videos at different clients. And so we have only normal cases during training. So we do a self-supervised training. And then during testing, we do a zero-shot classification of normal versus abnormal.
Okay, thanks.
Thank you.
All right. Thanks a lot, and good luck for your defense.
Thank you.